Hero methods accomplish many things. Machine learning, reinforcement learning, computer vision, and natural language processing are all methods that learn from experience, and as such, they're known as learning methods. Monte Carlo methods, continuous simulation or dynamic networks, and discrete event simulations are all about, as their names suggest, simulating a system. When considering which hero method to choose, it's very useful to think of what each method will accomplish. Understanding of what each method will ultimately accomplish is also key when attempting to put different methods together in an architecture to solve a complex problem. In this section, we'll present the 7 types of methods based on what they accomplish. Keep in mind that, as always, the methods outlined in this section are meant to be illustrative, not exhaustive. You can find additional learning resources for each method in our glossary if you'd like to enhance your understanding. And of course, Kato's built on its forms. Use them as a wealth of information and insight. What does it mean when we say that a model learns from experience? The system architect doesn't teach the model anything formal. Rather, the model learns from, and subsequently the model's entire world is defined by, the data used to train it. The model has access to past experience and history to be used as training data, and long-established learning techniques are used to understand and discern any underlying patterns. The understanding and recognition of these patterns are codified as intelligence, so that the model knows what to make of data when it is encountered in a post-training environment. Let's take image segmentation as an example. There are several ways to segment an image. One way is for the model to determine which segment each pixel belongs to. This is an approach from the ground up, and segments are formed by combining pixels that the model thinks belong together. Another approach to image segmentation is from the top down, where the model identifies regions in the image that are different from one another. Whether the method your model uses is classical or cutting edge, image segmentation is often modeled as a learning problem. Learning models are created for specific purposes, and as such, the purpose of your model varies based on the type of method selected. Take, for example, the popular method machine learning that allows for learning the relationship between a target and a set of factors. In medical applications, it could be about determining a patient's cancer diagnoses based on a panel of medical tests and exams. In financial trading, it could be whether to buy, hold, or sell at any time based on factors such as the current prices of securities, market indices, or specific economic conditions. More broadly speaking, if the model is used to learn a discrete value, it's akin to classifying a dataset as one of several classes. If the model is used to learn a continuous value, it's a regression model. Given that the choice of targets and factors is made by the modeler, its learning is said to be supervised. For example, you develop a model that's tasked with cleaning those areas flagged as dirty. In some instances, the objective is to learn the relationship between a set of variables with no particular target. In those cases, the model is directed to elicit patterns inherent in the data on its own. This type of learning is unsupervised. For example, you leave a learning model in an empty room with all of the pieces, tools, and assembly instructions to an IKEA dining set. If it figures out the relationship, great. If you end up with an AI art sculpture, also great. Let's dig into a couple of other types of learning models. Deep learning is a set of techniques that perform machine learning using deep neural network architectures. Outside of regular machine learning problems, deep learning models may be used for learning sequences or time series. Because deep learning models must identify the next items in a sequence, they maintain and track the internal state of the system. Take, for example, a model that predicts the outcomes of a basketball game based on sequentially tracked game statistics. This model would need to identify what the patterns of the data are and also maintain the internal state of the system. If you feed the model all of the potential data available from the game, names, heights and weights of each player, points scored, rebounds, steals, blocks, time of possession, etc., a deep learning model would be able to identify the patterns that occur and predict an outcome of the contest. Computer vision has its roots in signal processing. However, the most sophisticated computer vision methods are learning-based. This method involves making sense of objects in images and videos. In relation to our predictive basketball model, computer vision might be able to take the base model to new heights. Where the model might have previously only analyzed alphanumerical data fed to it, computer vision would allow the system to analyze game tape further to understand the nuances and potential outcomes of matches down to the possession. Similarly, the best natural language processing methods are also learning-based. Where machine learning is based upon analysis of past data, reinforcement learning teaches the model how to perform actions based on how they affect the environment and on what rewards they bring. The model learns from experiencing the world. In this case, the learner model performs actions in the world and collects the new state from it. Actions that bring positive rewards are favored, and those that do not are ignored. Back to our basketball example. Reinforcement learning could be used to build models that understand the game, but in this instance by interacting through play. Sure, they would have to learn all of the basics first, but eventually reinforcement learning could allow for models that play the game, officiate, or even coach. A triple threat. Here are the key closing notes on learning methods. Learning models are primarily data-driven, though some have been extended to utilize formal knowledge representations or take explicit direction. Learning models behave like black boxes, as we noted in our previous image segmentation example. As long as the job is done correctly, the internal workings of the black box are not of concern. Kato AI.